Hey folks, welcome back. Today we're going to start with electrostatics, which is the study of charged objects and how charged objects interact with one another. Sounds fantastic, right? Yes, it does. Let's do it. First and foremost, what does it mean to have a charge? It's kind of like mass in that it's just a property of matter. It's just something that an object has. And that's about as much as we know about it. So protons have a certain positive charge, electrons have a certain negative charge, and we don't fully understand why or what charge is. It's just a property of it. Now this property is measured in units of coulombs. If you remember in the fall semester, literally everything could be broken down to kilograms, meters, and seconds. And now we're throwing a totally different unit in there. So a coulomb does not have anything to do with these other things. It's just that property of charge. How do you measure its intensity? It's in units of coulombs. And all that it really does is tell you the excess or the deficiency of electrons within an object. So the only way to gain a charge, to gain a negative charge, is to take more electrons on. The only way to gain a positive charge is to lose electrons and leave behind protons, so you've got a net positive charge. And that's about it. So when we talk about protons and electrons, it's kind of helpful to start with this idea of what's called the elementary charge. So the charge of a proton is the charge of an electron, except one's positive and one's negative. And that value, which you don't have to memorize, I'll just be sure to give it to you on a test or anything like that, but it's probably good to have written down. The charge of a single electron is negative 1.6 times 10 to the negative 19 coulombs, which means the charge of a proton is positive 1.6 times 10 to the negative 19 coulombs. Now a couple of things about this. One, the symbol for charge is Q. Why is it Q? I have no freaking idea, but it is. So Q is the symbol for charge. A lot of times you might just see a little lowercase e. Now this lowercase e simply denotes that, well, it's just a special symbol for the charge of an electron. So if an object has, let's say, plus 3e, that just means I've got a net charge. It means I have a deficiency of electrons. I've got a charge of 3 times 1.6 times 10 to the negative 19 coulombs. And that's what that means. So if you see little e in the context of electrostatics, that's probably what it means right there. So yeah, protons and electrons have the same charge, but they got different masses. So be aware of that. And meanwhile, neutrons are just neutral. They just hang out there. A little more about charges, some of the nature of how charged objects work. 1, all charge is quantized. And by quantized, I just mean that it has to be an integer multiple of the elementary charge. You can kind of think of it like a stepladder. I can be on step 2, and I can be on step 3, but unless I'm a wizard, I'm not going to hover anywhere between steps 2 and 3. That's impossible to do. I've got to be on either one or the other. Similarly with charge, I can either have gained an electron or gained 2 electrons or gained 3 or 4, but I will not have gained 3.5 electrons. So I'm not going to have a net charge that's 3.5 times that elementary charge. Another thing about charge is that it is conserved, which means charge doesn't just come out of nowhere. It has to be from the exchange of these charged particles. And the total charge of a closed system remains constant. Let's say I got a system, and inside the system I have but 3 objects. 2 of them are negatively charged and 1 is positively charged. The total charge of this whole system, well, 2 minus 3 is negative 3. Right? So that means this total system, if you look at all these objects together, there are 3 more electrons than there are protons, basically. Now, let's say I let all these objects collide, bounce off of one another. They're going to trade some electrons back and forth. Electrons will try to go from negative objects to positive objects. And then when all is said and done, they're done bouncing off of each other, then all 3 objects will have a new charge. Now if they've been in contact long enough and they're all electrically conductive enough, that charge will probably just be negative 1 for each of them. So that way the total charge of the system is still the same and they're all balanced among the objects. That's called equilibrium. that's not to say that's what has to happen. It's possible they'll bounce off of each other and I'll end up with a -1, a +1, and a -3. That's fine. But that's the idea of the conservation of charge. So within a closed system, that's going to stay consistent. Now all of this, as well as the next law that we're going to explore, was discovered by Charles Augustin de Coulomb. He was French, and he studied the torque on metal wires. He actually ended up determining the force between two charged objects by accident, like a lot of the most great discoveries. And here's what Coulomb's law is. So you all already know from probably elementary school that positives and negatives attract, negatives and negatives repel, and positives repel. But to what extent do they attract or repel? That's where Coulomb's law comes into it. It tells you the magnitude of the force between these two objects. Now they're both going to experience the exact same force. Doesn't matter if one has 1,000,000,000 times the charge of the other. From Newton's third law, object 1 and object 2 feel the same force. So here's Coulomb's law. F equals k q1 q2 over r squared, where q are the two different charges. So I've got object 1 that has charge q1. I've got object 2 that has charge q2, both measured in coulombs. K is this new constant called Coulomb's constant. It's simply 9 times 10 to the 9th Newton meters squared per Coulomb squared. And if you're playing along at home, you might have noticed that this is super similar to Newton's universal law of gravitation, which you remember, right? Of course you do. It's g m1 m2 over r squared, where g is 6.67 times 10 to the -11 Newton meters squared per kilogram squared. Now, a couple of things about this. One, electrostatics is so much stronger than gravity. Gravity, aside from the weak force, is one of the weakest forces that we actually know. It's just a huge deal when you get a really big mass, like the Earth compared to us. Meanwhile, electrostatics is way stronger. So if you imagine two protons, they both electrically repel each other, but they gravitationally, since they both have mass, attract each other. But we ignore that gravity part because it's so freaking small that we just consider two protons to repel each other. So that's one thing to know about it. The other is that, unlike gravity, I can both attract and repel with electrostatics. Versus with gravity, because there's really no such thing as a negative mass, there's only attraction between the two of them. So a lot of these problems are going to be really similar to when we did Newton's universal law of gravity. There's just one more thing to hold on to, and that's looking at the signs of the charges to figure out the direction of the force. But that's about it. So when I solve Coulomb's law problems, here are the steps that I like to follow. 1, I like to just straight up ignore the signs of the Q's to begin with. Forces are vectors, and as you all know, vectors, when they have a negative, it only indicates direction. If you try to throw the negative in mathematically, sometimes you will get f equals a positive number, sometimes you'll get f equals a negative number, but there's no one-stop shop to say positive means right and negative means left, because it doesn't necessarily. So the easiest way for me to do it is just ignore those negatives, just get the magnitude. Remember, vectors have magnitude and direction. So just get the magnitude, the absolute value, and then draw yourself a picture about where these charges are. And you all know from elementary school, again, positives and positives repel, negatives and negatives repel, positives and negatives attract. So if I'm trying to find the force on this one object, let's say on Q1, then I can use Coulomb's law based on the distance between them and the values of Q1 and Q2 to figure out what force that charge 1 is feeling. Then I just know that positives repel, so that tells me right off the bat what the direction of that force is. And that's all that you really need to know about that. Now, it gets a little more complicated when you have multiple charged objects all in the same space. And let's say you want to figure out the force on just one of them. Just like every other problem involving force, you're going to want to break it down step by step. So first, determine the magnitude and direction as if it was just between your object in question and one other one out there in the field. Then do that again for another object and another, until you have several force vectors acting on it at once. Then it's just a free body diagram problem. Take each force, break it into x and y components, add up your x's, add up your y's, and Pythagorean theorem that mess. So here's a quick little example of how that'll work. So let's say I got three charges out here, Q1, Q2, and Q3, and I want to know the net force on Q1. I also know the distances between Q1 and Q2 and the distance between Q1 and Q3. So first and foremost, any interaction between 2 and 3 doesn't matter. Doesn't affect Q1. Doesn't affect Q1, so I don't care about it. Now in terms of how to find the net force on Q1, first pretend that 3 doesn't exist at all. Just use Coulomb's law and find the force between Q1 and Q2. And that's just going to be K times Q1 times Q2 over RA squared. I labeled that F12, that's the force between Q1 and Q2. Now notice that it's pointing directly away from Q2. That's because positives and positives repel. Now I've done the same thing for Q1. Notice that it's pointing directly toward Q3. That's because positives and negatives attract each other. And I've labeled that F13. Now that's all I need. I can ignore everything else going on with Q2 and Q3. And I've just got an adorable little free body diagram on Q1. So now all I got to do is break down both forces into their individual x and y components, add up my x's, add up my y's, and I've got a grand total x, got a grand total y, Pythagorean theorem to find the grand total force on Q1. Not too bad. A couple of last things that I want to get to, and then we'll be done with this. This right here is the triboelectric series. It basically tells me if I rub two objects together, which is a good way to trade electrons and give them a charge. Think about rubbing your feet on the carpet and then touching the doorknob. You're definitely all charged up. This will tell you what is more likely to give electrons, what's more likely to take. So if I take a grocery bag that's made of polyethylene, that's a common substance for grocery bags, and I rub it against, for whatever reason, I've got a steel rod, then odds are the steel rod will give electrons to the polyethylene, because polyethylene is further down the chain than steel, and therefore the steel rod will become positively charged, polyethylene will become negatively charged. Now, if instead I take my steel rod and I rub it against my own hair, I guess, then the steel rod will likely become negative, my hair will become positively charged, just based on their relative positions on the triboelectric series. So that's how you use that. It may be worth taking a screenshot, just in case we ask these questions, but generally I'll give this to you if you need it. You don't have to write all of that down. There's grounding. Now grounding, it has a symbol that looks like a vertical line downward, a wire going downward to 3 parallel lines, decreasing in size as you go down. Essentially, it's connecting to an infinite reserve of charged particles called the ground. In reality, the Earth and its ground do not have an infinite amount of particles, but it's close enough. So it's close enough. And charges can freely flow between the reserve and the object, and they always try to reach equilibrium. They try to reach this nice balance. It can either be used to charge or discharge an object. Conductors and insulators you probably know a good deal about already. Both of them can either be neutral or charged, so don't think that just because something's an insulator that it can't hold an electric charge. That's not what that means. The method by which you charge it is different. We'll talk about conduction and induction later. The only difference between them is in conductors, charges can freely move around, and electrons distribute themselves evenly over the surface. Versus insulators, they do not allow charges to move freely, so once an insulator gets charged, it's just going to stay at the point where it was rubbed. And that's that. Finally, and we'll look at some demonstrations of this, polarization. Now, if there's a conductor, it can become totally polarized. What I mean by that is electrons are free to move throughout the conductor, so if I hold up a positive object near a conductor, all the electrons will come flying to that side being like, yeah, I want to get to those positive charges. And it'll leave behind a positive charge on the far side of the sphere. Now, protons are not actually moving around. This is all about the electrons. Protons are locked in place by their molecule structures. But electrons are typically free to move about an atom, since those are what are zipping around the outside. Now, if there's an insulator, it also can become polarized, but it can only become polarized, I like to call it a atomically polarized, down at the atomic level. So within individual atoms, the electrons are zipping around the outside of the nucleus, and so they can align on the far side of the atom or the near side. It's just that they're not free to move around the object entirely. So the polarization is a lot less dramatic in insulators. And we'll talk about this and its implications later. Until then, take it easy.